Greetings from cyberspace. Isn't this nice? You get to hear me outside of the classroom. We didn't quite get as far into the notes as I wanted to, so this is just a little bit to focus on what we're going to be doing tomorrow and your very nice little homework assignment you're going to be doing. Okay, we were talking about how we can represent vectors as arrows, as a stated magnitude and direction, and as the sum of the components. We're not going to worry about that one today. We'll come back to it. Okay, so I didn't have these slide up today, so this is what we mean by drawing a vector as an arrow. And that's what it is. Okay, it looks like a vector. It's going to have a certain length. It's going to have a certain orientation. And you're going to draw it to a certain scale. For example, in this case, the scale is 1 centimeter equals 10 newtons. So if we draw an arrow that's 12 centimeters long, or somebody shows us that arrow, we should interpret that to be 12 centimeters times 10 newtons per centimeter. So this would be 120 newtons. Oh, sloppy. This one, and the direction it basically is given to you right there. This one is another vector. It's 5 centimeters long. So we go down to our scale. We say 5 centimeters times 10 newtons per centimeter. So this is going to be a... I've lost it. There it is. So I'm still learning. 50 newtons. And of course, the direction is as indicated in the arrow. Okay, and this is another one we're talking about. This is an example of, okay, suppose I have a certain velocity and I want to say, okay, here's the magnitude, 20 meters per second. Here's the direction, 20 degrees above the x-axis. So if I had an x-axis, I would say that it's going to be 20 degrees. Okay, same with this one. Magnitude, direction. And you can use any angle that makes sense. So you can use negative x-axis if you want. You can use a y-axis if you want. Okay, now let's get into this tip-to-tail method. Okay, let's look at an example. I think that'll be helpful. Okay, just orient you. Okay, hiking trip. So this is probably one of the good ways to see how the tip-to-tail method works, because it involves displacement vectors. Group of hikers walks on a 3-day trip. They walk 8 miles one day to the northeast. On the second day, they travel 10 miles west. I guess they're camping. On the third day, they walk 12 miles northwest. What was the overall or net displacement on this 3-day hike? Okay, so these are all displacement vectors, but it's the same kind of rule for all vectors. Okay, let's get started. So first of all, since we're given directions like west and northeast and such, then instead of an XY coordinate axis, we want to think about using a compass, but it's really not different. You know, you've got this east-west line that could be thought of as positive x and positive or negative x, and this north could be positive y, etc. So it's really not that different. It's just we're just going to use the directions of a compass instead of our xy. But that tells us, okay, this is kind of our base here. We're going to start thinking about relative to the west. Okay, so first day, 8 miles to the northeast. Well, I forgot. Before we do that, we need a scale. So because of the size I have and the displacements I'm dealing with, I feel like this is an appropriate scale. 1 inch on my paper here will equal 4 miles of their actual travel. Okay, now I think we're ready. So start, and you can start with anyone you want, but I'm going to start with the day 1. And so I wanted to draw a vector that was 8 miles long, so that means it should be, this guy down here should be 2 inches. 2 inches on paper is equal to 8 miles. And northeast is halfway between north and east, so that's going to be essentially a 45-degree angle if we were thinking about, well, it's 45 degrees angle. That's what it is. Okay, now the second day, they walked 10 miles rather, due west. Due west. Well, 10 miles of displacement to scale is, let's see if I can do the math here, 2.5 inches. 2.5 inches. Okay, and due west means it's just due west. But notice that I started, the tail of my second vector starts at the tip of the last one. That's why it's tip to tail. Third day. Okay, they go 12 miles to the northwest. Well, that's 45 degrees. Of course, now if you're using a protractor, how would you get that angle? Well, you'd have to use your protractor and you'd go 45 degrees. Now comes the time for the resultant. Well, here's a nice way to think about it, because with displacement, you're saying like, okay, if I wanted to do the combined motion of all this, but in one single trip, I would start, if you say, tell someone, start where we left, and then go in a straight line and end up where we ended up. And that's going to be the net displacement. And when we're adding vectors, we often call that the resultant. So that's why it's an R. Okay, so the sum, the vector sum, that's called the resultant. It's not something that's really all that important. It's just a name. Think result. Okay, so now that let me get rid of some of this. Let's see, get rid of these marks I've made. Here we go. Okay, so now that this is what you're going to end up with on paper. So how do we scale that back up to our real problem? We want to know what's the net displacement. We don't want to know that there's a line on the paper, but what we're going to do is we're going to measure it for, excuse me, 4.8 inches. How are you going to do that? You're going to get out a ruler. You'll probably use centimeters, but it doesn't. Just measure how long it is on paper. Then you go back to your scale and you go in reverse. And you say, okay, what is 4.8 inches on paper equal to in the miles? So you basically take your 4.8 inches, whoops, multiply it by your scale factor, so each inch is 4 miles, and you're going to get 19.2 miles. So their net displacement, the magnitude is 19.2 miles. What about the direction? Well, you're just going to get out your protractor and you're going to measure the angle, and you can really use any angle you want, you know, relative to, you could have measured this from the north, you could measure it all the way from the east, but I always like to use the smallest angle, so I would use 48 degrees above, or we'd say north of west. Okay, I don't know if you can see that, but vector addition, next slide. Okay, so we added it day 1, day 2, plus day 3, because that's kind of the order. But it turns out we could have added up these vectors. We could have started out with the third day's displacement, added to the second, added to the first. We'd get the same thing. So just like regular addition is commutative, so is vector addition. And that just means it doesn't matter in which order you add these arrows, or which you line them up tip to tail. Or we could have gone day 2, day 1, day 3. Okay, here's an example. This is the way we did it on day, you know, in the days that they did it. This was day 1, day 2, and wait a second. That's in backwards order. Anyway, there's one way. I can't remember. Okay, when we add up the 3 days displacements, we get that. If we had changed the order around, oh, that was day 1. Okay, so I mean, that was in day order. Now the next one, I think okay, there's day 2 first, followed by day 3, and ending up with day 1. Completely different order, but notice, look, the resultant is the same. It's got the same orientation, and it's got the same exact length. So that is the same. It's that's what vectors are, the same if they have the same magnitude and direction. And of course, the other one, that's day 3, followed by day 1, followed by day 2, I think. They are commutative. Okay, another example. Well, there you go. You see that. There they are. They're all the same. So the order doesn't matter. Next example, we've got Gary is going to swim across a river. The river is flowing from the north to the south at a certain speed. So there's your, it's a velocity, right? Direction and speed. Gary is swimming in the water directly west. So he's going straight across. Well, that's what he wants to do maybe, but Anyway, that's his velocity. He's going in the water. In the water, he's swimming due west. But he's not going to go due west because he's actually being carried downstream while he's swimming across. We want to find Gary's velocity as seen from the banks of the river. That means we're going to add these two velocity vectors. Okay, so again, we're dealing with, instead of like x and y's, we've got north and south. Well, that's not really any different, except now we're going to think in terms of a compass. He's swimming west, so I'm going to draw that just to guide my thinking here. We also need a scale. Always, you can't do this without a scale. So 1 inch on my paper is going to equal 2 kilometers per hour. Okay, there is the velocity of the river, and I'm just calling that V1. No, okay, so here is what Gary's doing in the water. So relative to the water, he's going straight across, but of course he's not going to go straight across because the river's carrying downstream. So what would be the combined velocity of his velocity through the water plus what the water is doing as it flows down the river? Okay, well, we've gone, the first one is, so we basically have done, lay down the first one, doesn't matter which order, put the second one with its tail at the tip of the previous one. Okay, and now you always go back to where you started and you draw an arrow to where you ended up. Now, okay, not ended up like displacement, but to where the tip of the final velocity, the vector is. So there we go. This is the resultant. This is the sum of the two velocity vectors. We cannot simply just add the numbers. Okay, so again, how do I get information out of this? I have a line on paper now that is the sum of the two velocities. Well, you're going to get out your ruler. You're going to measure it. Okay, 4.1 inches. Then you're going to take that 4.1 inches and you're going to multiply it by the scale factor. Okay, so 4.1 times 2 kilometers an hour per inch, and his total velocity relative to the stationary the banks of the river is 8.2 kilometers per hour. And of course, in his direction, you're going to get out a protractor and you're going to measure, and that angle is 76 degrees. So we're going to describe that as, it's really 76 degrees below west, but because it's a compass kind of thing, we're going to use terms like south and west. Well, that's not a big deal though, because in fact, you're going to be using X and Y's axes for your activity. Okay, we'll do one more. Here is Pam. Pam is going to be shooting a basketball, so she's going to be exerting a force of 10 newtons at an angle of 50 degrees relative to the horizontal. Okay, we're just going to say that's the x-axis. The Earth is going to apply a gravity force of 2 newtons straight down. What is the net force on the basketball at this particular instant? Okay, so basically it means we're going to add these two forces. And again, they're vectors and they're not all lined up, so we cannot add or subtract 10 newtons from 2 newtons or vice versa. We're going to use the tip-to-tail method. Okay, no compass here. I probably should have put it here, so I'm going to go ahead and say, okay, there is the y direction. So that's everything, that's positive y. And here is our x direction, and that's of course positive, so I have it down here below. So that tells us our orientation here. Okay, we still need that scale. So 1 inch for this problem, I say 2 newtons works. Okay, so Pam, she's going to exert a force of 10 newtons at an angle of 50 degrees relative to the horizontal. Well, I know she's playing basketball, so I'm going to assume that means above the horizontal. So there's her push. Okay, so it's 10 newtons, so this should be 5 inches. And of course, how do I get this right angle? Well, I'm going to basically take out a protractor and I'm going to measure 50 degrees. Okay, now we're ready to take the second force and add it. Put its tail to the tip of this one. So actually, my coordinate axis is going to get in the way, but so I'm actually going to erase everything I've done here. I can do that. Erase. Okay, so now we got that out of the way. Now comes gravity. It's straight down, and it's going to be 2 newtons, so it should be 1 inch long. That's 1 inch. Okay, now the resultant. You go back to the tail of the very first vector, and you're going to draw an arrow with a straight edge, of course, until you get to the tip of the last one. Here it comes. Okay, now this, of course, is going to be our net force. Now, how okay? So what do? Now I have this line on the paper. It's an arrow. It's a directed line segment. Well, you're going to get out your ruler. You're going to measure 4.3 inches long on paper. You're going to go back to your scale and say, okay, 4.3 inches times my scale of 2 newtons per inch, and the overall force on this basketball is 8 newtons. Okay, direction. Once again, you're going to use your protractor, and I think in this case the positive x-axis is the most convenient starting point, or on reference frame, place in which to measure your angle from. I'll try to say that better. And so it's going to be 42 degrees above the positive. We want to always indicate, are we talking about the positive axis, x-axis, or on the other side it could be the negative. Okay, that's it.